So the topic of our discussion today is really going to be water. And then we'll start talking about some calculations that we can do. We'll start by only doing them with water, and then we'll move on to some other examples. But the idea that we're going to try to get across is that the properties of water have a really huge influence on climate. So we know from the questions we just answered that climate is the average temperature precipitation conditions over time. And being around water has a really big effect on that. One of the reasons why is water's very high heat capacity. Now, heat capacity has to do with the idea that we need large amounts of energy to change the temperature of water. And very specifically, when we look at heat capacity, we'll see that, we'll see that the value for the heat capacity for water is 4.19 joules per gram degree Celsius. So what this really means is that that's how much energy we need to change 1 gram of water by 1 degree Celsius. Now 4 doesn't really sound like a lot, but if you think about what 1 gram of water represents, 1 gram of water is 1 milliliter of water. That's a very, very tiny amount. And so even to take a small cup of water would take a few hundred joules of energy to change it just by 1 degree. And if you wanted to change it by more than 1 degree, it would take even more energy. So the idea is that if I have some water and I'd like to change its temperature, compared to other substances, I need a lot of energy. And so we're really going to focus on this idea that it's not that 4 is a big number by itself, it's that compared to most other substances, this is the big one. This is a huge number. So if we take a look at the picture that's at the bottom of this screen, there's water, there's air, there's sand. Now, I imagine that a lot of you have been, whether it's somewhere tropical or just somewhere in Canada in the summer, you've been at a lake or at an ocean when it's hot outside. Is that something that's familiar to most people? You've been there. It's happened. Now, if you haven't, you got to go on vacation more, I guess, a little bit. But this, you don't have to be at a tropical beach to have this scenario happen. Let's say that it is a very, very hot day. Now here's what you will probably notice. The air feels hot. The sand feels hot, but the water feels cold. That's generally the scenario, even if you're somewhere that is a tropical location, the water will feel cold. Even places that supposedly have very warm water, the water's not warm. It's not like stepping into a bathtub. It's cold, usually initially. And the reason that on a hot day, the sand feels so hot, sometimes so hot that you don't even want to step on it, and the air feels hot, but the water feels cold, is that the air and the sand both have relatively low heat capacities. That means it does not take a lot of energy to warm 1 gram by 1 degree Celsius. But because water has that high heat capacity, it takes a ton of energy for water to change temperature. Now, especially in a scenario like this, where we're obviously on the edge of an ocean here, it would take an enormous amount of energy for you to even notice that the water felt warmer. And so the temperature of water is pretty cold even if it's really hot outside, because even though there's lots of energy around, it's still not enough to noticeably change the temperature of water. So what does this mean for us when we're talking about climate? It means that water stores heat. Because water absorbs so much energy to change its temperature, water has a lot of energy to give. And we've already briefly mentioned it, but what we'll talk about today is places that are closer to water have this effect of water providing a bit of heat to them. Either it's providing heat in the winter when the temperature is dropped, or it's moderating the temperature in the summer when more energy is available. But water stores heat. That means that the environment around water is affected by what the water is doing. So what we'll talk about is what happens when water absorbs energy and what happens when water releases energy. So kind of two sides of the same story. And we'll talk about it in terms of changing state, and then we'll talk about how we would calculate things with that. So we're going to talk about two different phase changes. When I say phase changes, I could say state changes, and I mean the same thing. I'm talking about water changing between solid, liquid, and gas. Now, the first one we'll talk about is the heat of vaporization. When we do a calculation, it will be abbreviated HVAP. H for heat, VAP for vaporization. Vaporization is evaporation, which is probably the term that you use the most with water. It's the idea of making a vapor out of a liquid. So the heat of vaporization is the energy needed to change 1 gram of water from liquid to gas. So just like with the heat capacity, we'll be measuring this based on 1 gram of water. Now, there are other ways that you can measure this. You can measure it for each mole of water instead of each gram of water. We're just going to focus on the gram part. So if you happen to perhaps talk to someone who goes to a different school and is calculating it with moles, that's a valid way to do it. There's more than one way that you can do this, but we're going to focus on grams so that it lines up with heat capacity. Now over here on the side, I'm trying to illustrate to you what is happening when water is evaporating. And the idea is that vaporization happens when water molecules get enough energy so that they are moving quicker. So vaporization really is just quicker movement. So the difference between a liquid gas molecule and a gas molecule is simply how fast they're moving. And we know that anytime something is moving, that's based on kinetic energy. So don't forget that when I measure the temperature of something, what I'm really measuring is the kinetic energy of the particles of that substance. That's what temperature really is. So in the top picture up here, I'm illustrating to you little water molecules. And the idea is that evaporation happens when a molecule can get away from the neighboring molecules. So if we look down here, water evaporates when the molecules absorb enough heat to have sufficient kinetic energy to break loose from their neighboring molecules. If you recall, water molecules are attracted to each other. So in our unit on biology, we talked about how water molecules are cohesive and adhesive. Because they're polar, they have these forces that attract them to other water molecules and that attract them to other substances. So if I'd like my water to evaporate, it has to absorb enough heat so that it has enough kinetic energy to break loose from those forces, those bonds that are holding them together. So water evaporates really slowly if you just leave it to its own devices. Water will evaporate eventually if you are just letting it mix with air, and the air is room temperature air. But water will evaporate quickly if it's heated. The idea is that if there's an additional source of kinetic energy, well, then things will happen faster. So remember, energy doesn't come from nowhere. If I'd like my water molecules to evaporate, they have to get heat from somewhere. It can't just mysteriously happen. So here are a couple of ways that this heat can be obtained. Sunlight, of course. And that's a major way that water is heated if we take the globe as a whole. The air at the water's surface. So we know that heat can be transferred through fluids. Water and air are both fluids. So if there's warm air, some of that heat could be used to heat the water that's at the surface. Or it can come from other water molecules. That means that a water current could bring warm water molecules to a place where there are colder molecules. And some of that warm water could transfer its energy to the cold water. Remember that energy is never coming from nowhere. It's always being transferred or converted from something else. When heat is being absorbed from other water molecules, they lose energy and cool. So if warm water flows and helps bring heat to some colder water, and then some of that water evaporates, well, that water that was warm is now cool. The term for that is evaporative cooling. Now, because of this, because when some water evaporates, kind of necessarily other water cools off, this helps keep bodies of water relatively stable. So because this energy is constantly being transferred from one water molecule to the next, the temperature of water really does not change very easily or very quickly unless we add some additional source of energy. Now this is all about water changing state from liquid to gas, but I want you to know that everything that we've said here, the opposite would be true if water was to change from gas to a liquid. So when it rains, that's condensation. And condensation is when water goes from a gas to a liquid. So it would be the opposite process. Now when water changes from liquid to gas, it has to absorb energy from its environment. But when water changes from a gas to a liquid, the opposite happens. Water releases a little bit of energy, and what this means is that the air around it is a bit warmer. So, when water evaporates, the air around the water should be a little bit cooler because the water is absorbing energy to change state. When water is changing from gas to liquid, like when it rains, and the same would be true if it was snowing or any kind of precipitation, the air around the water should be a little bit warmer because the water is losing energy instead of absorbing it. Now that's the change between liquid and gas. We'll usually talk about heat of vaporization, but just remember that the opposite is true as well. Does anyone have any questions that they'd like to ask here? So then the opposite of this, or not the opposite of this, but the other thing we would have to discuss is the other state change that happens, and that would be the change of state between solid and liquid. So before I go there, is there anyone who's still writing stuff who'd like this up still? So the other thing that we would discuss, which is actually very similar, is water's heat of fusion. This is the energy needed to change 1 gram of water from solid to liquid. So the word fusion could be used. We could also talk about melting here. We're talking about the change of state from solid to liquid. So water has a high heat of fusion compared to other substances, just like with heat capacity. And so it takes a lot of energy to change 1 gram of water from solid to liquid. Now, in both of these heats of fusion, heat of vaporization, the temperature is constant. So notice that I didn't say how much energy it took to change the temperature by 1 degree. That's what heat capacity is. Heat of fusion and heat of vaporization only have to do with what state the molecule is in. And what we'll see is that anytime something is changing state, its temperature will stay constant while the particles are changing state. So what effect does this have on climate? Well, in the spring, snow melts. Now, if there is a lot of snow, what that means is that lots of energy needs to be absorbed from the environment. The result is that if there's a lot of snow that has to melt, instead of the sun's energy being used to warm up the air and make it seem like summer, a lot of the sun's energy is going to be used to melt the snow. So the result would be the air would stay cooler. So if you were to compare two places that had relatively the same climate, except one had more snowfall than the other, and I'll pick two places, here and near Edmonton. My parents live near Edmonton, and when the snow started falling, it never went away. They don't get Chinooks like we do where the snow all melts. So when it comes to springtime, my parents have a snow pile as tall as me in front of their house, and my snow pile is only about this high. We have less snow here. It's going to take less time to melt the snow, which means that it will start getting warmer sooner here, partially because of that. That's not the only reason, but that would be a factor. How much snow there is to melt will affect how long it takes for the weather to really start warming up. Now, as winter sets in, we could talk about what happens there. In winter, water freezes, which means it releases energy to the environment. So if you live close to a large body of water, like a big lake or a river, or if you were to live close to an ocean, As winter sets in, water will start freezing, and it takes a lot for water to freeze. It takes a lot to heat it up, which means it takes a lot to cool it down. So as the air around the water is getting cooler, the water will start freezing, but it will release energy as it does that. The result is warmer air. So, if you live somewhere near a large body of water, you will probably have warmer air in the winter because the water will give off some of its heat. If you live somewhere where there's a lot of snow that needs to melt, it will probably take a little bit longer in the spring for the temperature to seem warm because the snow will absorb a lot of energy to melt before the air around it can warm up. Does anyone have any questions that they'd like to ask about either vaporization or fusion? Oh, by the way, I didn't just put this picture here because I saw this. Someone sent it to me. That's my dog. I have a little tiny miniature dachshund. She won't even go outside right now because if she walks in the snow, it covers her because she's only this tall. So I open the door for her to go out and she looks at me and says, "Are you kidding me?" Which is more or less what this dog is saying. I thought it was cute. So I'm going to pause here and give everyone some time. So if you go from left to right in this picture, heat energy is taken from the environment. That means that the air gets colder. Along the bottom, we're saying if you go from right to left, heat energy is released to the environment. That means air gets warmer. The idea that you should use to sort of maybe sum this up is that whatever's happening to water, the opposite will be happening to the environment. If water is warming up, well, it has to get that energy from somewhere. It must be taking it from the environment around it. If water is cooling down, well, the energy can't disappear. It's the laws of thermodynamics. So that energy must be going to the environment. So this summarizes solid, liquid, and gas states and what happens to heat energy as you change state. So I'm just going to pause. All right, I'm going to start talking again. So this sums up what is happening if I were to ask you with words. And this is where the quest that you are having on Friday ends, at this explaining part. The stuff that we'll do next, the stuff that has to do with actual numbers and calculations, won't be on the quest that you're doing on Friday. It will be on the test that we do next week, but you'll have more time in between. Now, if you have printed out the notes, we're actually going to skip the next two slides just for now because I want to try to do the whole calculation example in the same class rather than having it be split up. But we'll come back to them. So we're going to talk about how do we calculate these three different things that we've just discussed for water. How do we calculate its thermal energy based on heat capacity, and then how do we calculate what's happening when water changes state? So the first thing that we're going to calculate is thermal energy. And this is the formula that we're going to use to do it. Now, in your data booklet that you got at the beginning of the year, there's a formula sheet, and on it, at the very top, is this formula, as well as the other two formulas that go with vaporization and fusion. And then near the bottom of the formula sheet are the constant values. For example, I already wrote down the value for water, 4.19, but there's a few other constant values that are on there that we'll end up using either on practice questions or on quizzes or on tests. So we'll talk about this formula. Q is thermal energy. This is measured in joules, just like all of the other types of energy that we would have discussed in our last unit. So realistically, if I can calculate the thermal energy that something has, and its energy is converted into another form, well, it's already in joules. Now, M in this formula is mass, and mass has to be in grams. And I want you to notice this difference. In the physics unit, mass had to be in kilograms because that's what the units were based on. In this calculation, mass needs to be in grams because of this little letter C. This little letter C is heat capacity. And the units are joules per gram degree Celsius, and I'll just write that up here. Because heat capacity is based on grams, our mass has to be in grams as well. Now the delta T, I'll just come over here so I have some more space. Remember that the triangle, the delta means change in, and the T means temperature. So we will be using degrees Celsius as our temperature unit. And since it's not just temperature, but change in temperature, that really means final minus initial temperature. So you'll always be subtracting final and initial. Now what does this mean? This means that this can be negative. Your temperature could be lower at the end than it was at the beginning. So if I asked you what is the change in temperature, it would be legitimate to have a negative number as your answer. Mass cannot be negative. If you get a negative number as the mass, something's wrong. You can't have negative mass. That's not a thing. That just wouldn't happen. It's not possible. Heat capacity should also not be negative. Because by definition, heat capacity is how much energy does it take to raise the temperature of 1 gram by 1 degree Celsius. The other thing that can be negative is Q. So the idea is that if the change in temperature is negative, Q should be negative as well. If Q is negative, so should the change in temperature. So they should follow each other because they're the only two things that could be negative. If one of them is, then the other one kind of has to be as well. Now, just so that you know, if Q is negative or if it's positive, has a different meaning. If you were to calculate Q, the quantity of thermal energy, and you got a negative number, that means energy was released. If Q is a positive number, that means energy was absorbed. Now, most of the time we'll be talking about water. It's not the only substance in the world, it's just the one that we talk about the most because of its effect on climate. Now, this idea about energy being released or energy being absorbed, this particular idea is the one that carries through. So this formula, you'll use it if you take Chem 30. It's the very first part of the very first unit. And understanding whether or not energy is released or absorbed is actually a really big part of that, which is why I like to talk about it here. Now you'll notice that I gave you examples of some other values. I don't need you to memorize heat capacities. What I wanted to show you was that lots of substances have really small numbers as their heat capacity. If we take a look, aluminum is 0.93, lead is 0.130. Copper is actually relatively high, it's 3.85, but not many things are as high or higher than water with their heat capacity, which is why water has such a huge impact on climate. So the first example is just to make sure we know how to put numbers into the correct spot, and then we'll do a few more where we rearrange the formula. In the first example, I have 50 grams of water. So there's my mass. Now, I'm going to highlight the fact that it's water. A lot of the time it will be, but some of the time it won't be. It doesn't have to be water that we're talking about. So just be careful, which substance are we discussing? It's heated from 25 to 50. So that means 25 is initial temperature and 50 is final temperature. Now this little part in the middle probably won't be written most of the time. In a lot of the practice questions, I write down what the heat capacity for water is, but very much like gravity in potential energy calculations, I would assume that you can look on your formula sheet and find this value. So this particular part will not always be there in the question, but you would always have the opportunity to look at your formula sheet and find the heat capacity of water. So our goal is to determine the value for Q, and a lot of the time that will be your goal. That means you write the formula exactly the way it is, and then we would simply need to fill in the correct numbers here. So our mass was 50.0 grams. The value of C, which is the heat capacity, is 4.19 joules per gram degree Celsius. And the change in temperature is final minus initial. 50 minus 25 is 25. So those are the numbers that I'm going to multiply together. Now when you put this in your calculator, what you actually get as your answer needs to be rounded off because of significant digits. So what you actually get is 5,237.5. Now because I was calculating Q, my unit is joules. So anytime we're calculating energy, joules is the unit. I have two choices for how to represent my answer. I could either leave the unit as a joule, or I could change it to kilojoules. So I'll show you two possible ways. Way number one would be to write 5.2 times 10 to the power of 3 joules. That would be me taking this decimal and moving it 1, 2, 3 spots. Since I moved it 3 spots, I would write 10 to the power of 3. That's where that power of 10 comes from. Now I could also simply write 5.2 kilojoules. A kilojoule is 1,000 joules. And unless I've specified which unit you have to use, which I don't usually do, you could report your answer either way and they would both be correct. Now, would anybody like to ask any questions about any of the maybe units or significant digits or anything that's in this formula so far? So here are the other 3 examples. Example number 2 is asking you how much thermal energy. So that's Q. I'm going to leave that one alone because it follows the same pattern that we just did. And I'm going to focus on example 3 and 4 first because these ones are asking us to do a calculation that's slightly different. Example 3 is asking us to calculate the change in temperature. That means I would like to know what is delta T in this particular case. So if I start with my original formula, and I decide that I'd like to know what delta T is, it has to be all by itself on one side of the equation. That means I have to divide both sides by m and c. If I do that, they'll get canceled out on the side that they were on originally and end up underneath q. So to calculate delta T, you'll do q divided by m and c. Now, when you have two things on the bottom of a fraction, I want to remind you, use brackets in your calculator. If you don't, your calculator might not recognize that both of the things are supposed to be on the bottom. You're supposed to divide by both of them. And you might end up having the wrong answer, even though you've written the steps out correctly. For example 4, we're asking you what is the specific heat capacity of a particular substance. So here, we are not looking for delta T, but we are looking for C. So you would have to rearrange the formula in a very similar way to what you did in example number 3. So I'm not going to rearrange it for you just yet. I will show you in a minute, because I'd like to give you the chance to try it yourself first. All right, I'm just going to run through how to solve these 3 problems. If you've already gotten them and you're working on the review sheet, you can keep on doing that. That's totally fine. For the first one, the numbers that you would have used would have been 28 grams, 4.19 joules per gram degree Celsius, and negative 10 degrees Celsius. Notice that we use the word decrease. So sometimes you are going to actually have to read English words when we're doing calculation questions to see whether or not the number should be positive or negative. So just be careful, especially with temperature, because it could go up or it could go down. The other clue that your answer should be negative is that it said in the question, energy was being released. That means that your value for Q has to be negative. Now in the second one here, so example number 3, to calculate the change in temperature, I would have taken not 8.38 kilojoules, but 8,380 joules. It makes a difference because the value for C is measured with joules. So I would have taken my energy in joules, divided it by my mass times my heat capacity. Now, because my heat capacity has joules as part of its unit, Q has to be in joules as well. They have to be the same unit. So there's my calculation. I just want to remind you, make sure you put brackets on your calculator. Otherwise, your calculator's not going to know that you meant for 4.19 to be on the bottom. In the last question, similar thing applies. 21.6 joules divided by, in brackets, 2 grams, and this time positive 24 degrees Celsius, because it said the temperature increased, not decreased. And that's how I came about this answer, 0.45.